Recording has started.
Alright, let's talk about the write operation. So now you want to write the data in. That means you want to flip the data. For example, initially, if the N1 stores 0, N2 stores 1. Now you want to write the new data in. So you want to change the N1 from 0 to 1 and change the N2 from 1 to 0. So this is the new data you want to write. Then what we should do is to provide the new data from the outside of the array. So that means you have to make the data ready from the outside of the array, and you want to write the data in. So that means you need to apply VDD to the BL and ground BL bar. This is the data you want to write in. After you make this ready, then you can turn on the WL again. You need to turn on the WL from 0 to 1. Now something will happen here. On the left hand side, you will see this is the same as the read condition, because you apply VDD here, and then this is VDD, this is 0, so you still have this current flow as before. But this will not make the N1 node flipping from 0 to 1. Why is that? Because as we just discussed in the read condition, you don't want this happen in the read. It's the same configuration as the read. If you only look at the left-hand side, you compare this slide and this slide. They're exactly the same configuration. So if here the N1 increase of the voltage is very minimal, then during the write operation, this N1 will not increase too much. That means 0 will not increase to 1. 0 will increase a little bit, but not to 1. 1 means VDD. Maybe only increase 10% of the VDD or 20% of the VDD, but it will not change to VDD. Because this is by design. Nothing will flip. So what makes write possible is on the right hand side. If you look at the N2 node here, now the PG2 will be turned on because this is VDD. Now you ground here, and then N2 initially store 1, so this is VDD. So you see the N2 transistor is turned on and actually is in the saturation because this is VGS, like VDD, and here VDS, VDD. So PG2 is turned on, and you should have current flow from N2 to the BL bar. And also the PU2 is turned on. PU2 is a PMOS, and its gate is attached to the N1. N1 is attached to the PU2's gate. So this is 0. And then this is VDD, power supply. So the VGS for the PMOS, we only look at the absolute value, right? So this is like VDD for the VGS of the PMOS. So this PMOS is turned on, and the PMOS is in the linear region. So you will have current as this this green path shows. You have this current as well from the power supply to the BL bar. So you have this current flow. This current is going to make the VDD of the N2 decay. It's like discharging the N2 load as well. And we can also use the resistor divider model to look at this right hand side. So here on the right hand side, we care about this PU2 and this PG2, and this is your N2 node. So initially this N2 is 1, and we want it to change to 0. So if it's a voltage divider, how do you make the N2 close to 0? You have to make the RPG2 smaller than the RPU. So this is the voltage divider, and if you want this N2 voltage to be small, then this resistance, the PG should be small, PU should be larger. And it can be translated to the PG stronger than PU. Or in other words, the conductance of the PG2, that is W over L PG, and then W over L PU. You want this to be larger. But here, not only the W over L matters, but also here you see the PG is NMOS, PU is PMOS. So actually it's mu N larger than mu P. Previously, for this one, actually we should also carry the mu N and mu P. I didn't do that because in this case, the pull down and the pass gate both are NMOS, so it doesn't matter. So you have mu N on both sides. But here, if we consider the conductance, then you have to consider the ratio of the NMOS and PMOS mobility. So mu N is larger than mu P. Even though the W over L can be the same, then this condition is still satisfied. So if you can make the N2 voltage small by sizing or even you don't do the sizing, by utilizing the mobility difference, you can make the N2 node close to 0. So if N2 is close to 0, then something will happen here to the PU1. So let's assume the N2 is already switched from 1 to 0 due to the ratio between the PU2 and PG2. Now the N2 is close to 0, then the PU1 will be turned on. Why is that? If this is 0, then this is 0. So here this is 0. So the PU1 is a PMOS, right? So this is VDD. So the PMOS, the absolute value for the VGS is VDD. So that means the PMOS is turned on. So if this PMOS is turned on, then you have current, this additional current here, this arrow. This current will be flowing into the N1 node. That means the N1 voltage will further increase. Because previously by the current through the PG1 only will not charge up N1 voltage. But now you have additional current from the PU1, so the N1 voltage will further charge up. That's why the N1 can flip from 0 eventually to VDD. So you finish the transition. Now N1 switch from 0 to 1. But there is an order for this process. So that must be N2 1 to 0 happens first. And then the N1 0 to 1 will follow. So then we finish the write operation. Eventually then you flip the data, like N1 switch from 0 to 1, N2 from 1 to 0. But this 1 to 0 will happen first. So here then we can define this gamma ratio as well, and we have talked about this earlier. So basically if you care about this here, the PU2 and PG2, then we can have this voltage divider as we just discussed. N2 node, and then this is a PU, and this is a PG, and we just said that the resistance of RPU should be larger than resistance of RPG to make the N2 close to 0. Then we can translate that to the mu N W over L PU smaller than Let me see. So this is smaller than mu. Sorry, this pu is pmos, so it's mu p, w over l mu pu, and smaller than mu n, w over l pg. So we define this gamma ratio, which is this w over l pu divided by the w over l pg. So this ratio will be equal or smaller than 1 to make this condition satisfied. It can be 1. The reason is that even there's the same w over l, so basically those two w over l equal to each other. So even you have the same w over l, because mu p is smaller than the mu n, so this condition is still valid. So it can be equal or smaller than 1 for this gamma ratio to make the right operation possible. And then we can also look at the timing diagram for the right operation. So we can recap what happens to the right. So the right, you need to prepare the data from the bit and bit and bar. So if you want to write the data 1 to the BL, sorry, you want to write the 1 to the N1, then you will prepare the BL to be VDD. And then the BL bar should be ground. 0 will be written to the N2. So you need to make the 1 and 0 ready, complementary to each other from the BL and BL bar. And then turn on the WL. So here you turn on the WL. And then the process will happen as we discussed earlier. So the N2 node will first have the 1 to 0 transition. So the N2 voltage will have 1 to 0 transition first. Till the N2 voltage decay to a small value, then the N1 0 to 1 will happen later. So you see this is 1 to 0 happens first, and N1 0 to 1 will follow. And after this process, then the data is flipped. You have the new data written. So this is a write operation. Any questions? If the SRAM original stores 0, how do you deal with writing 0? So this is a good question. So if you, there are two ways to deal with this. One is to read before write. So every time you can read before write, so that means you have the new data, which is from your, for example, the output of your logic module. You need to write this new data in. Then what you can do is to first read the cell and then compare the old data with the new data. If the old data and new data are the same, then you don't need to rewrite. This is one way. The other way is no matter what, you will overwrite of the old data. Then even though here you don't change anything, you can still prepare the new data. For example, in our example here, N1 stores 0, N2 stores 1. Then your new data, if it's still 0 and 1, let's say the BL is 0, BL bar is 1, you can still prepare the new data from the BL, and then you can open the word line. Then nothing will happen. Nothing will happen. So then you after the write operation, then you keep the data basically. All right. Any other questions? Okay, so let's have a summary. And for the SRAM, here's the read operation. We actually care about this 0 to 1 disturbance. So what is this 0 to 1 disturb? So this is what we discussed here. So when we read, this 0 of the N1 node will increase a little bit. And we rely on this current to increase the N1 node. At the same time, this current is going to decay the BL voltage. So we rely on this disturbance to the N1 node to read out the data. But we don't want this N1 to increase too much because we don't want to change the data. This is what we need to care about the read. And then for the write, as we discussed, the N2 node 1 to 0 transition should happen first. And then the 0 to 1 will follow. And actually, you will see there's a fundamental conflict between the read and write. Why is that? Because for the read, we need a large beta ratio, larger than 1, which means we want a stronger pull-down, weaker cascade. But for the write, we want a smaller gamma ratio. That means we need a weaker pull-up, stronger cascades. So you see that for read, we want a weak cascade. For write, we want the strong cascades. Then this is a fundamental conflict. And essentially, if you think about this problem, the read and the write will always conflict with each other. Why? The read, you don't want to read, you do not want to change the data, right? The write, you do want to change the data. So one is no change, the other is change. Because both read and write process will go through the cascade transistor. So the cascade is shared in the read mode and the write mode. Then one is to change the data, the other one is no change the data. Then you have the fundamental conflict. Or in other words, you can think this way. You have this latch in the middle, right? And then you have this cascade. So this latch in the middle is where you store the data. This is the memory state. That is a stable circuit. Then the read operation. So basically you want to provide a bridge between the internal states that you store here to the external outside world. So then you just want to have a weak link here to detect what's inside. So you want it to be weak. You don't want the outside noise or whatever to flip the internal state of the memory here. So you just need a weak cascade. On the other hand, for the write operation, you do want to change the data that is internal here. So the external data is coming from the outside. Then this external data needs to be coupled to the internal node strongly through the cascade. So in that case, you need a strong cascade. So you see the fundamental conflict here. To make the SRAM working, the typical ratio of the W over L could be like PD over PG over PU is like 2:1:1. Why would this work? I just draw half of the circuit because the other half is complementary. So here, this is a PD, pull down, cascade, PG, and pull up, PU. So pull up is PMOS. If you have two of the W over L for the pull down, and then one for the cascade, and then one for the pull up, then you can satisfy the condition here. Because if you look at the read path, which is the PD over PG, you do have a stronger PD, weaker PG. Both are NMOS, so the difference comes from the W over L. And then for the write, then you care about the PG and PU. You want a stronger PG, because PG is NMOS. So even though they have the same W over L, so PG should be stronger than the PMOS PU. So this is a typical ratio you can use. And this can be for your L3 cache. Because here this is like a minimal size, minimal W over L ratio. And then for the L3 cache, you want a larger capacity. That means each cell should be minimal size. So this can be the L3 cache. Minimal W over L ratio like 2:1:1. But if you want to design L1 cache, what can you do here? You still need to satisfy this relative strength of the PD, PG, PU. But for L1 cache, what you care about is the speed, because L1 is closer to the processor. You want it to be fast. And we discussed earlier the rate speed. How do you make it fast? Here. How do you make it fast? You want to size up the transistor, the pass gate, so you have larger current. Then if you have larger current, then you can make the delay smaller. So you need to size up the transistor here. So for L1 cache, what you can do, you can, for example, use 4, 2, 2. If you do 4, 2, 2, still relatively speaking, the pull down is stronger than pass gate, and pass gate is stronger than pull up. So then this is still satisfied. But the W over L is increased. So you can pass larger currents, then you can charge and discharge faster, then you can make the speed faster. So this is good for L1 cache. Then the trade-off is now use larger transistor. So the area of the memory cell will be larger. Then the L1 cache capacity will be smaller. Because given the same chip area, then if each cell is larger, then the number of cells will be smaller. That's why the L1 cache, the capacity is small. So L1 cache, is faster in speed, but small capacity. L3, you minimize the area, so you can have large capacity. But relatively, it will be slower. So no matter L1, L2, or L3 cache, no matter which cache, they all use this 6 transistor SRAM. So from the circuit schematic point of view, they are the same. The only difference is how do you size the W over L for different levels of the cache to balance the speed and your capacity. So any questions here? I think that's all for the SRAM's lecture. So if you do not have more questions, we are going to stop here for today. All right, then thank you. Bye-bye.